Okay, let's do more examples. Right. The following graph shows the decomposition of gas A according to the following equation, A giving you 2B plus D. The decomposition is conducted in a 2 decimeter cubed container. So here they're telling us the volume of the container of the reaction. Now, if you look at this graph, first of all, ask yourself, is this the reactant or product? And since it's decreasing, it has to be reactant because reactant always decreases. Right, let's look at number 1. Calculate the average reaction rate. Now they want average reaction rate, which means we're going to be drawing a secant and we are going to involve two parts or two times on a graph. And they said they want it in moles per second. Now moles per second is not concentration, it's moles, which is moles per time. So we're not doing concentration, we're doing it in moles. And since from the graph we have concentration, we need to convert the concentration to the moles. Right, and they want it from time is equals to 5 and time is equals to 35 seconds. So this is the time period we're going to do it for. Right, now let's look at this graph. Basically, we're drawing a sequence. So here is the graph. Now they want from 5 to 35 seconds. So you're going to draw a graph or a secant from 5 seconds. So there's 5 seconds to 35 seconds. And you're going to draw a line joining this graph. Right. And now from here, we can get our values to do the calculation. Now, since they want moles and not concentration, we first have to get concentration and then convert it into moles. Right. Now, to do that, we're going to use the formula N is equals to CV. Right, and the volume they gave it to us in the beginning of the question, they said it's 2 decimeter cubed. Right, so we're going to look at the moles at 5 seconds. So here's it here, the concentration at 5 seconds, it's 0.8 and that's concentration. So to convert it to moles, we're going to multiply it by volume, which is 2, and we'll get 1.6 moles, and this is at 5 seconds. Right, at 35 seconds, the concentration is 0.2 and we need to convert it to moles. So we're going to say 0.2 times 2, which is the volume, which will give you 0.4 moles. So now we have the moles at 35 seconds and the moles at 5 seconds. And now we can work out the actual rate of reaction. So what we're going to say is it's change in moles over change in time for reaction rate. So here we're dealing with moles. It's going to be the final mole, which is 0.4 minus initial, which is 1.6 divided by 35 minus 5, and that will give you negative 0.004 moles per second. And can you see it's a negative answer? Because again, we're dealing with reactant and reactant is decreasing. Right, let's look at number 2. Now they want instantaneous reaction rate for the reaction at 10 seconds. Now, if you're getting confused about the average and instantaneous rate, average rate, they will always give you two numbers. So from 5 seconds to 35, like in question 1. For instantaneous, they will always give you only one time. Right, and here they want it in moles per decimeter cube per second, so it's in concentration, so we don't need to change anything. Right, so they want it for 10 seconds. So here's the graph. And can you see at 10 seconds, this is where you're going to touch the graph. Now you're going to draw a tangent because now it's instantaneous rate of reaction. And the tangent is going to touch at 10 seconds, which is what they want. And we're going to draw a graph which is touching that point. Now, everybody will draw a graph in different positions and everybody will get different points where the graph starts and where the graph ends. Here, they started it at 2.5 seconds and they ended it at 20 seconds. But if you draw it, it might be different, but it doesn't matter. Your answer will still be the same or similar. Right, so again here, reaction rate is equals to change in concentration over change in time. The concentration at the end here will be 0.1, which is from the graph of the tangent, minus the initial concentration, which is at the beginning, 0.8, divided by the change in time, which is 20, here where the graph ends, minus the beginning, which is 2.5, and this will give you still negative 0.04 moles per decimeter cube per second. And again, it's negative answer because the reactant is decreasing. Okay, now let us move on to something which we call the collision theory. Now, first of all, we're talking about the rate of reaction and all of those things. But what is actually a reaction and how does it happen? Now, a reaction is basically when you have reactants and they turn into products. Now, for the reactants to turn into products, the reactants first have to come into contact with each other. They have to touch each other, otherwise they're never going to form bonds between it to become products. Now, if you look at this picture here, you're dealing with nitrogen oxide and ozone. These are the reactants, and they need to come into contact with each other in order to form the products, which is nitrogen dioxide and oxygen. Now, when they come into contact with each other, we call that the collision theory. Collision means to collide, to bump into one another, to form direct contact with each other. So the reactants must come into direct contact with each other. Now, there's two things that's needed for that direct contact or collision to happen. The first thing is they have to have enough energy. Now, obviously, in order for atoms or molecules to move, they need to have energy, and the type of energy they need to have is kinetic energy. Now, how do we know if reactants have enough kinetic energy to be able to come into contact with each other? And that's where we come with activation energy. Remember, we did that before. Now, activation energy is the minimum kinetic energy needed for reaction to happen. So if the reactants have enough kinetic energy, which is either equal to or more than activation energy, then they will be able to move close to each other, and then they will be able to collide with each other and probably form products from this reaction. Okay, so the first thing they need is kinetic energy, which is either more than activation energy or at least equal to activation energy. The second thing that they need is the correct orientation of the collisions, which means when they collide with each other or when they directly contact each other, they can't just do it in any way. They need to be in a proper orientation. Now, if you look at these pictures here, can you see you have the two reactants and they're colliding, but can you see it's what we call an ineffective collision, which means they collided, but they didn't collide in such a direction or orientation where they actually form products. So when an ineffective collision happens, there is no reaction. There is no reaction happening and you don't form products. It's almost like a lock and a key. If you put a lock in the right way, if you put a key in a lock, it will open it. But if you put it upside down or a part where it doesn't fit, it's not going to work. It's not going to open the door. So the same thing with reactions. The reactants have to collide in a correct orientation. Then only will they form a reaction and form products. So if you look at the second one, now you change the ozone. You made it the other way around compared to this one's. And now when the two reactants collided, it actually collided in a way where they fit into one another to form bonds and to make new products. And this is what we call an effective collision. So basically, you need two things. Energy, which is kinetic energy, either equal to or greater than activation energy, and the correct orientation. If they can collide, even if they have a lot of kinetic energy, but they don't collide in the correct orientation, then they still won't have any products. So basically, reaction rate is directly proportional to the quantity collisions per unit time, which is directly proportional to particles that have kinetic energy greater than or equal to activation energy, and that is directly proportional to particles which correctly orientated. So basically, only when you have enough kinetic energy and then they collide in the correct orientation, then only will you have a effective collision, actual successful reaction, and then the reaction rate will increase.